Hello everybody. Today we will talk about popular CV problems, about training process and about evaluation of the model. We can solve a lot of problems by using machine learning methods. And classification, detection, segmentation, tracking and pose estimation problems are among them. Let's look into each of them. The classification problem requires an answer to the question: is there in the picture an object that we would like to find? It may be a cat, a person, a dog, a bike, etc. The next one, detection problem, requires not only the answer to this question, it requires to predict certain bounding boxes where this object is. That's why we need to calculate pixel coordinates of every object in a picture. The third one is segmentation. Picture segmentations allow us to highlight every pixel that belong to our objects. So, for example, if you want to find scissors in a picture, this method will highlight every pixel of scissors in this picture. The second one, tracking problem, it is a detection problem that can differ different objects that belong to one class. It is needed to identify these objects over the time. The last one, pose estimation, is identifying of key points of an object in a picture. It allows to find a pose of an object. All of these popular CV tasks can be solved by machine learning, as I have already said. And the main point is to estimate the model's predictions. So for us, it is easy to look at the picture where there are two models' answers. The green bounding boxes are predictions of the first model, and the red ones are predictions of the second model. So we can make a conclusion that the green predictions are copes with these tasks. So this model can estimate every cat in this picture, but the second model do it worse. There are some predictions where there is not a cat in the bounding boxes at all. As I have already said, it is no problem for us to select the better one. However, neural networks are arranged in their own way. That's why we need a special tool for estimating the prediction of the model, which will be understood by the model itself. And this tool is loss function. It estimates the quality of model's predictions. It takes two numbers, model's prediction and a correct answer. After that, it's comparing these two numbers and returns the resulting loss. As we have already learned, the model's predictions depend on the input information and the weights. That's why we can say that loss function depends on the weights. What we are doing through the learning, we are trying to decrease values of loss function by adjusting the weights. And there are a lot of types of loss functions, and their choice depend on the problem. Here we can see three examples of loss functions: mean squared error, mean average error, and cross-entropy loss. What we can say about the first one? In these examples, y sub I is the answer of the model, and y sub I with tilde is the correct answer. Mean squared error returns a big value in model's mistakes. It is not suitable for image restoration, for example, where shape color gradients are blurred. There we can use the mean average error, and it will cope with this task. And the last one, cross-entropy loss, is suitable for classification tasks, for example. For calculating the loss, we propagate our input information through the whole neural network. And this process is called forward propagation. The result of forward propagation is the model predictions. Then we can take the output and compare it with a correct answer, then apply a loss function to the model's output and a correct answer, and get the resulting loss. After this procedure, the model is able to estimate its errors. There you can look at two graphs of learning. In the first one, on the left side, loss function decreases through the learning, and it is okay. It's what we want. However, on the right side, the loss function does not decrease through the learning at all, and it is a bad example of training process. Let's imagine we have a model with only one weight, makes some predictions on only one picture, using different values of this weight. After doing them, the model can get a loss and takes derivatives for each value of this weight. The derivative will describe the behavior of the function. The derivative at the point shows us the direction of this function in this point. In geometric representation, it is a tangent to our function. In the left point, function decreases because the derivative at this point is negative, and the derivative that is taken at the right point is positive. That's why we can say that the function increases at this point. After dealing with this information, we can assume that there is a minimum between these 2 points. Now we can find this minimum, this pit, and that what we want. We want to roll into this pit. To sum up, we want to find a point where derivative will be a 0 and the second derivative will be positive. It was a simple variant of derivative. For multiple variable functions, there is another representation of the derivative. It is the vector that shows us direction of the function. It consists of partial derivatives. Every partial derivatives show the direction along its variable. Multiplying it by a unit vector along the axis of each of the variables and getting the resulting sum gives us this vector. It is called gradient. And the method that was created for adjusting the weights for each of the neuron connection is called backpropagation. It is based on these derivatives. This process starts from the output and goes to the input. It takes the partial derivatives through the network, and after this calculation, it is possible to identify what actions with weights will lead us to the loss decreasing. We need to change them proportionally to the derivative with a minus sign. What's more, the derivative of loss function just shows us a direction. It shows us if the loss function increases or decreases. But we need a certain step for weight change, and this parameter is called learning rate. It allows us to control weight change. It saves from 2 big steps in situation where derivative value is huge and represents a useful tool for balancing between speed and stability of convergence to the minimum of loss. Each picture is a special case, and it does not have to contain some helpful patterns for the formation of our generalization. What's more, there can be some outliers in our datasets. All of these cases lead to incorrect weight change and make it difficult to find a minimum of loss. It confuses the model, but we also have a solution. Let's look at the concept, which is called batch. This concept allows you to average gradients across multiple images. It reduces weight modifications and makes the training process less sensitive to outliers. How does it work? Through the learning, the model calculates derivatives for several images in parallel, and after getting them calculates the mean gradient. In this way, the model relies on knowledge about the selection of images during each change of weights. Of course, parallel computers require additional GPU memory. These concepts of training process help to find a minimum of loss. However, it's much more difficult to find a minimum of loss function because it is necessary not to stay at local one. What's more, we are finding a minimum in the space of the number of weights dimension. It contains non-trivial cases that make it difficult to find the right direction and the value of the most suitable step for decreasing loss. Regarding these problems, optimizers are used. These entities allows us to find the right trajectory of moving to the minimum. Difficult cases are shown in these pictures. Point is able to be in the minimum along the one axis and not to be in the minimum along another. So we need to explain the model that it is bad to oscillate along the axis where it is already at the minimum. And we need to ask it to go down along the another one. And it is really hard to do. It requires additional information for algorithms to make the right choice of direction. That's why we're happy to have optimizers. There are different variants of these entities: SGD, stochastic gradient descent, momentum SGD, momentum stochastic gradient descent, and the last one, ADAM. So they are suitable for different tasks. I think that the most complex is the last one. Okay, let's look at the simple task where optimizer can help us. There are different situations and we need to behave in different strategies with them. For example, if we are at the beginning of the learning, we need to have big steps to go rapidly to the areas with minimums. But when we are going closer to these minimums, we need to change our strategy. We need to make steps slower, to make learning rate slower. It allows us not to stagnate near the minimum. It allows us to get into this minimum, respectively. What's more can be done to improve the training process? We can increase the datasets, change loss function or optimizers, or to increase the number of steps that are done by the training process without changing anything else. This concept is based on one meaning, epoch. It means training through the whole dataset you have. After training this model on your whole dataset, you can repeat the process. The model can look at some pictures in a different way, because its recognition ability will be increased after passing through the whole dataset. What's more, the order of the pictures can be changed in the next epochs. It contributes to finding patterns that are helpful for your generalization, rather than to specific patterns of your own dataset. Let's look at the simplest task of computer vision. So, a binary classification. We want to answer the question, is there an object in a picture? A cat in our case. And there are only two possible answers. The cat is either present or absent in a picture. Let's look at our training loop that allows us to solve this problem. It looks like this one. We select the number of epochs, then take our dataset with pictures and answers about the presence of the object in the picture, tell the optimizer to reset derivatives, and this operation should be done at every iteration during the training with batch size equal to 1. However, if the batch size is 8, if we want to average the derivatives through every selection of 8 pictures, this operation will be done after every 8 iterations. Then we calculate the output, return loss from the loss function, apply backpropagation method, that is, calculate derivatives and get new values of weights. And at the end of this iteration, move our weights to new values. As I have already said, models can learn specific patterns of your dataset, rather than patterns that are helpful for your generalization. So, and this problem is called overfitting. Here you can see two lines. The green line is an approximation of our model. It is the boundary between red points and blue points, because in binary classification we have only two variants of points. In this example, red and blue, respectively. And the black line is the boundary that is valid for other data, that is helpful for our generalization. So here you can look at these two variants of the result of our training. Okay, you can see a red point among blue ones, and it is an outlier. It is a mistake in our dataset. It may be the mistake of people who make a set of answers, or it may be not a mistake at all. This point can contain more patterns of another class, and it is okay. What is important that our model can understand that it is an outlier, or it can decide that this special case contains the main patterns of its class and make a mistake. We are trying to avoid this situation by splitting our dataset. We split it into two sets. Training set that is used for finding patterns in our data, the validation set that it is used for checking overfitting, and the testing set that is used to qualifying the results of our learning process. How validation works? It shows when we need to stop the training process. Okay, there are four types of points in a binary classification. The first one, true positive, the second one, false positive, the next, true negative, and the last, false negative. True positive describes the situation when there is an object in a picture and model confirms this information. The second one, false positive, it's about the case where there is not an object in a picture, but our model thinks that there is. True negative describes the situation when there is no an object in a picture and model confirms this information. And the last one, false negative, it is about the situation where there is an object in the picture, but model denies this information. And using these types of points, we can understand how good was our training process. In the ideal situation, we have points that belong to only two types of this variant, true positive and true negative. But it is impossible. We will always have a bit errors in the model's answers. The main purpose is to decide which of them are okay and which are not. For example, we deal with the cancer recognition task, and here it is okay to have a couple of false positive predictions. They will force a person to be checked for cancer once again. However, false negative answers should be strictly prohibited. A person will not start treatment and it may lead to lethal consequences. There is a tool, a cool tool, which is called confusion matrix. It shows us a number of points that belongs to each of these four classes, four variants. But what about metrics? We want the numbers that will be meaningful. And there is important difference between loss function and metrics. Loss function shows us a direction of our training process of the function that we want to decrease. And the number of loss function, the values of loss function are useless. However, we want to find numbers that will be meaningful and will describe our results respectively. Here we can see a pool of these classification metrics, and accuracy, precision, recall, and F1 are among them. Accuracy shows the proportion of correct predictions. Precision tells about a number of true positive and false positive answers. Recall about the true positive and false negative. And F1 score is used in these balanced data sets, for example. It shows the average proportion of correct predictions through classes. Choice of metric depends on the purpose of training. Today we discussed the main components of the training process. That's all I wanted to say. Thank you for your attention.